Okay, here we go. The first one about pressures. It says pressure and flow of gases. Let's just reiterate. We're going to talk about buoyancy and water properties. That's all we're doing out of this ILM with you guys. So if you're a note taker, it might not be the exact same. These particular objectives are not the same, but we are going to do objective 1 here, where it says describe chemical properties of water and the effects of hot water heating systems, temperatures in there. We're going to do state the 3 laws of buoyancy and the effects of buoyancy on regular shaped objects submersed in water. And that's it. That's the 2 objectives that we're covering in this ILM. And I think that's the objectives in your ILMs. Is that correct? Can somebody please confirm that for me? Yeah.
Mine says something different.
What does it say?
Describe the chemical properties of water and the effect of temperature in hot water systems. State the 3 laws of buoyancy and describe the effect of buoyancy on regular shaped objects submersed in water.
Oh, okay. That sounds like 1 and 2.
That's the, oh, never mind.
That's exactly the same objective. Okay, excellent. Well, good. Thank you for that. So this module starts, this does start with fluids and physical laws relating to gases and water, right? Water is the primary fluid in the plumbing trade, and you're responsible, look at that, you are responsible for its care, transportation, and disposal. I guess that describes what we do for a living. I've never really described as care, transportation, and disposal. But that's what we do. All right. So first off, we're going to talk about a little bit about properties of water in this objective 1. So properties of water, the chemical symbol, as you know, is H2O. So 2 hydrogen ions there and 1 oxygen. So that's why they call it H2O. And this is a compound, right? We know that this is a compound. It has 2 separate things. It's a compound, and it is the most abundant compound on Earth is water. And while we're on what's Earth does, do we know the air in our atmosphere, what it's made of? Does everybody know our atmosphere? Do you know what our atmosphere is made of?
Nitrogen.
Anybody? What's that? Nitrogen? 79% is nitrogen.
Oxygen.
And then there's oxygen. And we have about 20% oxygen. And then now after that, we have about 1% other stuff. Okay. So there's a little bit of breakdown of our atmosphere, what's in it, what's not in it, similar to that. So when these positive and negative charges get together, see, they have negative and positive here. When they get together, they produce a very strong molecular bond, right? When they float around in the atmosphere and they collide together, they're very sticky to one another. That's why we have that. And they exhibit strong cohesive forces together, right? When they're all together. Now, when we start talking about cohesion, that I would say mercury has very strong cohesive forces because it likes to stick together. It's kind of like the T-1000 Terminator. He likes to be molten something, mercury. And In a tube, we should point out that in a tube where we have water or mercury, mercury will produce, because of its cohesive forces, a convex meniscus. CUS. And however, water in a tube, because of its adhesive capabilities, will produce a concave meniscus in a tube.
Hey, you want to know the cool way to remember if it's concave or convex?
Sure.
I don't know if it's like not a big brand of skateboards, but there's a skateboard brand called Concave. And the skateboard looks like concave, and convex is just the other, like, is backwards. You know what I'm saying?
Yeah.
You know what I mean?
So happy concave.
Mm.
Okay. So water is, oh, thanks for that. Water is also known as the universal solvent, right? Because we use water to wash down everything, to cut acids and everything. We just use it all the time, right? So let's go to the next page here, and chemical properties of water. We use the term pH, and that tells us the level of acidity or alkalinity within a solution. And we have a measurement. So pH is basically measuring how many hydrogen ions are present. That's where we get a pH balance. It's the presence of hydrogen ions. Okay. Now, hydrogen ions in here, it says that water molecules consist of 2 atoms of hydrogen, 1 of oxygen. We know that, H2O. But the pH of water can be broken down into a couple of parts. They are hydrogen ions and hydroxyl ions. And this is where we get these little extra hydrogen ions flying around. As you can see now here, we show this atom. It's a neutral atom because it balances out between the protons and the electrons, and that's why they call it neutral. But if you have extra electrons flying around on here, it becomes negative. Electrons are negative and protons are positive. Quite frankly, if you look at this pretty closely, if you make this middle here, if you make this the sun, and these are all the planets that are going around the sun. Oh, wait, our planet is not flat, by the way. Just want to throw that out there. It's kind of like the orbits that go around our sun. It's very similar. Can you imagine that, eh? It's all the same. From the big to the small, it's all the same. Anyhow. Always fascinated me as a child when they first came out and they showed me this molecular thing and atom components. I'm like, well, that just looks like our solar system. And then my teacher like, Doug, you just sit there and don't tell me anything. I'm like, well, I don't know why. So listen, when heat or energy such as heat is added to an electron, it starts to move at a higher energy level, meaning it starts to go farther away from its center. Okay, and we have this little electron. As we heat it up more and more, it can actually be cast off, right? So it can be flung off there because it's going so fast. And then the atom now becomes positive, right? And it will pick up little extra electrons as it's going through its thing. But as it's heated more, it will lose these negative electrons, and any atom may now pick up that free electron. And now if an atom is negative net, meaning has more electrons on it, it becomes a negative ion. So that's kind of what happens when minerals are introduced into our water, right? We have all these extra little things going on in there. And this way, we can determine whether, now, I'm not going to go on to talk about how it's actually done, but we can determine whether something is acidic or alkaline, okay, by these hydrogen ions. Now, they go on to start talking about most people have experienced acid indigestion. That only happens when I drink too much red wine. It's high in acidic, right? It's always acidic. And you could take what's called an antacid or Tums or whatever, but that's really an alkaline. And what it's trying to do is just balance out all of those electrons in your belly. Okay, that's what happens. Now, this pH scale. We have this pH scale here, and I want to point out that number 7 is neutral. This is where we go for number 7. It's neutral. And I want you to pay a little extra attention here. Let me see if I could zoom in on this a little bit more. There we go. So as we go this way with a lower number, more acidic with the lower numbers. Above 7, you become alkaline or a base. And this is to deal with how many hydrogen ions. As you can see here, from 7 to go to 6, so there's 6. Let me just, it's 10 times more hydrogen ions from one step to the next. It's 10 times more from 6 to 5. Between 7 and 5, it's 100 times more. So I just want you to see the level of hydrogen ions in each number associated with it. That's what it's trying to tell you. Okay, does that make sense? All right. And as you go down to alkalinity is 10 times less. Every step, every number on the pH scale is 10 times less hydrogen ions. So that's what I wanted to point out there. Now, we know that pH can be done with litmus paper, yes? Litmus paper tells us the level of acidity. We just dip a piece of paper in and it'll turn color. Has anybody not seen litmus paper? If you're treating boilers, if you're treating swimming pools, if you're doing that kind of water treatment stuff, you would know what pH is. You can, there's all different kinds of tests. There's electronic testers, etc. But that helps us to determine what we need for treatment. And trust me, water treatment is big business, people. If you want to actually have some kind of niche part in the plumbing world, water treatment is extremely lucrative, especially in Southern Alberta. Southern Alberta has some of the best water and some of the worst water because of the mineral and gas content in the ground. Okay. We'll talk a little bit about that coming up. But I do want to talk about, in this particular picture here, you can see number 7 right here. Number 7 says pure water. And as you move up to more, 10 times more hydrogen ions, they talk about urine and saliva. Now, because of the high level of acidity in urine, we cannot use copper for drains for urinals, right? Does anybody know that? That's why. because the high acid content will eat that copper drain. It reacts badly. That's why in commercial applications, it's either plastic or cast iron, right? On urinals, right? So that's why we have to do it. No copper allowed on drains for urinals. Look at black coffee is also highly acidic. It says in there. Now, coffee can give people acid indigestion because of its high acidity. Now, there's a coffee place right in the Aldred Center called Second Cup. I can't drink their coffee. It's too acidy for me. I hate it.
Have you ever had the brownies?
What?
Have you ever had their triple chocolate brownies?
No.
Dangerous.
Look at this body. Does this look like I eat triple chocolate brownies?
Yeah.
It doesn't happen by accident. Just kidding.
Hey Doug, is this chart be available to us? Because it's not, I don't see it in the new book at all.
No, you don't have it. I will put it in the I'll put it in the chat. But guess what? Where it is in D2L under water properties and buoyancy. You will see the handouts, and this table is in it. Okay. Now look at tomato juice. Acid rain is very acidic. Does anybody know how we get acid rain? Way back when we're starting to really use gases to burn stuff and to gain energy and burn coal, highly sulfuric coal. Well, all that stuff went up in the atmosphere and it was very acidic and it became acid rain, and it started to destroy forests in Ontario, maple tree forests where they did a lot of the, maple syrup harvesting of the sap. Well, it started killing all the trees and stuff because of the stuff we were putting in the atmosphere, and it was coming back in rain. Terrible. Look at this. Grapefruit juice, orange juice, very bad. Look at lemon juice, super acidic. And this is not good for your teeth either. So if you guys drink a lot of juice, use the little straw that comes with your little juice box, right? To protect your teeth. You want your teeth for as long as you can live. Trust me on that. As an older guy, you want your own teeth for as long as you can. So take care of them. Try not to drink a lot of juice. Use a straw, that sort of thing. It's bad for your teeth. It'll take a. Anyways, look at your stomach acid, super acidic. And then we get to like battery acid, which is, well, it'll eat your genes right off your body. You get that stuff on you. If back in the day when I used to fill up my battery with water to get that, I don't know, that's old school. You guys wouldn't even ever do that anymore. And then we go the other way. Alkalinity, look at baking soda, Great Salt Lake. Does anybody know what milk of magnesia is? It's an antacid, right? It's like a Tums, but it was like a milky chalk substance. Yeah. Ammonia, soapy water. What? Soapy water is a base. Did you know that? Does anybody know how soap actually works? Well, let me tell you. So when you're using soap on your hair, your oily hair, what happens is this alkaline, wow, I don't know what happened there. Touch the button. This alkaline, which is soap, actually sticks to the oils because the oils are a hydrocarbon, right? Almost, if you will. It's got that slippery kind of. Anyways, what happens is they stick together because of their negative and positive charges. And then when you wash it away, that soap takes that oil off of you. That's how soap works. It just sticks together. It's a chemical bonding between the oils and the soap, and it just, and as you rinse water on it, they stick together and you can wash them off. That's how soap works. You ever seen the commercials where they're washing baby ducks in oil? Like, who does that? Who dips their ducks in oil unless they want to eat them? I mean, come on, why do they show that on TV? These little baby ducks all in oil, but they use soap to strip the oil off of the baby ducks, right? Everybody's seen that commercial, little baby ducks. We're gonna eat them later. We're gonna deep fry them, little baby ducks. But regardless, it's cruel commercial. I don't know why they get away with that. How they can, dip baby ducks in motor oil and then try to clean them. I don't know. You should complain. All right, and then we get down to the bottom here. Look at liquid drain cleaner. Has anybody used chemical drain cleaning supplies?
Strike.
Yeah, it's pretty awful shit, man. I don't ever recommend you use that kind of stuff. If you can get it, if you can avoid it, please do, right? I hated chemicals in the drains because I never knew if I had to go to a house and they say you're fixing a sink and they're like, oh yeah, it's plugged. I use chemicals. And I hated that because half the time nobody ever told you they used chemicals. And of course the trap is full of chemicals and then you have to take it apart. And yeah, it's just, all that kind of stuff. You know what I'm saying? All right. I'm going to pause right here. Okay, we're going to kind of pick up where we left off here. And that was from that scale that we talked about over there. So we're down here and it says in here, there's a lot of words in this, but since the relationship between hydrogen ions and hydroxyl ions in a given solution is constant for acidic conditions, we can measure the acidity or alkalinity, right? That's what we do. Now, it says the strength of the acid depends on the degree of the ionization in water. A strong acid will have ionization rates approaching 100%, while weak acids between 1 and 5%, the acids might ionize. Okay. And then they give you a little bit of weak acids and what they are. Alkalis are the other end of the scale, right? And they kind of give that as well. Now, what's important to us is this right here. In the pipe trades, the pH of water impacts piping and equipment. Acidic water has a corrosive effect. And before I continue on, there was a situation in Langdon several years ago when I was in the trade, well, in the field, I should say. We replaced about 12 hot water tanks in Langdon, just our little company itself. And it's because their water treatment tended to get a little acidic and it would eat out hot water tanks like crazy. Right? They kept it a little acidic to kill off some extra bacteria, but man, did it have a detrimental effect on hot water tanks there. I mean, it's good for me because it was all, money, but still. So this is important to us, right? Where we have high acidic places or materials or fluids running through our piping and our systems and our equipment, it can cause problems. Now, on the other end, if it's an alkaline water, it has a tendency to deposit scale on the inside of piping and equipment, right? And that's not good either. And in copper exclusively, a pH of 8 or greater will result in a copper oxide film forming on the internal pipe walls, and it acts as a barrier and reduces the rate of oxidation. So this is a problem in our field. So again, water treatment is very important. So water hardness, we indicate water hardness by the presence of dissolved minerals. Why do we have so many minerals in our water? Does anybody know?
It's all mountain runoff.
Well, that's right. All our water comes from the Rocky Mountains. The water runs all over those rocks, all of those minerals, picks up all of those ions and everything else. And this is why we have hard water here in Southern Alberta. It's a big deal, right? And these minerals can have a detrimental effect on both the water use and on actual piping and equipment. Hard water tends to leave that or reduce the cleaning ability of soap and detergents. Does anybody have a water softener in their house? Anybody? 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 No? Well, if you ever use softened water, it leaves a little bit of a slimy film on you, but man, can you get a soap lather going. Let me tell you that. The bubbles are like 5 times as much as hard water. So, you know, it's my soap and I could use as much as I want, right? But it will, if you have hard water, the soap and detergents just don't work as well because it inhibits the transfer of that ions and that stickiness that the soap happens to take away the dirt. Okay, it just happens. And that's why. Now, in addition, these minerals can coat the inside of pipe and equipment, reducing, this is the big one, flow and heat transfer. Now, in smaller equipment like instantaneous hot water tanks or flow through boilers for domestic hot water, this is a big issue. Because after a year, you're going to get a call saying, you know, my hot water tank, my Navian boiler, whatever it is that you're using, they're going to call you and say, it's not really working as well as it used to. Well, it's because that thing needs cleaned. The heat exchangers inside of these small flow-through boilers are made of very thin copper, right? Very thin copper. And if you put hard water through there, that copper will get coated on the inside, affecting the heat transfer to your water at the end use. So these boilers need to be serviced and cleaned constantly. Some of these boilers or these small flow-through boilers, they won't warranty them unless you have a water softener before it. They want you to use softened water. They want less minerals in the water. All right. So again, this is big business. Marty is a little bit better at cleaning these boilers, et cetera, than I am. So you could talk to him a little bit about this in heating class. All right. This is a big deal for us. This is a problem. Okay. So these dissolved minerals, as the water passes through the ground on rocks, etc. So this one says water that is passed through chalk or limestone will have large quantities of chalk and limestone in it, right? Water that passes through iron or ironstone may have rusty appearances. So we use the term hardness to designate how much of these dissolved minerals contain. And there's 3 designations. So here's the 3: temporary hardness, permanent hardness, and total hardness. And there's a lot of jokes in there, but I'm not going to do those jokes because, you know, they refer to being old and young and whatever. Anyhow. So total hardness, it tells us that they use a scale, and they use this thing called ppm, and it's parts per million, and they use that. And so this little classification table right here, softened water has very little hardness in it, moderately soft, hard, very hard. And listen, very hard water, when you get up to this kind of stuff, it might not be potable. So before, we know what potable means, yes? It means drinkable. It means consumable for humans, is potable water. Now, a bunch of wells, if you are servicing a well, or if you're digging a new well in Southern Alberta, you have to submit a sample of that water to the government for testing to ensure that it's potable or suitable for human consumption. All right. So there's that as well. So the total hardness of water is made up of some temporary and some permanent in varying proportions. Temporary hardness is called the bicarbonates of calcium and magnesium that are dissolved in this water, causing that temporary hardness. But here is the deal. Anytime that you get water at a temperature of approximately 140 degrees, this temporary hardness starts to settle out of the water as scale. Has anybody ever seen the white scaly stuff on aerators or end of taps or whatever? That's what it is. All right. And that and I can tell you, I've made tons of money on just replacing aerators for people, because some people just don't want to touch their plumbing fixtures, so they will call a plumber in and say it's just not working the same, and you just take the aerator out, put a new one in, and they are happy as pie. You know what I mean? Just saying, it's part of it. Okay, so any temperatures above this inside of a hot water tank will become coated, drastically reducing the heat transfer capabilities. Okay, we talked about that a little bit, and that is a problem. And so that's why we like to treat water. Now, permanent hardness is the carbonates of calcium, magnesium, in addition to sulfates, nitrates, chlorides, and other elements. Now, this chlorides do not set out of the water as scale deposits unless you get hotter. So this is a problem for boilers, right? This is where it happens. And this is where we get that sludge inside boilers and inside our piping system. This is what it's from. And
Sorry,
you,
Doug.
Yep.
My sheet says 175 Celsius to 350 Fahrenheit.
Huh.
Does it really make a difference between that 148 and
It's
the
hot. It's hot. It's got to be above. What they're saying is this is above 148.
Okay. So there's not a difference between the one that mine's stating and yours is stating, just because it comes up on a test, right? I want to make sure which one I should, if I should
Sure.
test mine out, put yours, or.
Yeah, you could put this one. I'm not going to ask you temperatures,
Okay.
but I will ask you what is permanent, temporary, right? And that sort of thing. And I'll ask that, but I won't ask for temperatures. So this is the problem. And so we have blowdowns on steam boilers to remove that stuff, etc. I would talk to Martin about boiler maintenance issues. Now, for any reason, if you're coming to an old boiler system and then they want to start treating that boiler water with chemicals, well, listen, man, things will break down in a hurry, right? Some of your equipment, your zone valves, your pumps, etc. Things are going to start to fail once you start treating old boilers with chemicals, etc. So make sure you build that into any kind of quote. etc. If you're going to clean a boiler, you must say that, you know what, eventually anything mechanical will break down. We start treating your old boiler with these chemicals, etc., to take some of this stuff away, you're going to expect to have other problems. I just don't want anybody to treat a boiler and expect nothing to happen afterwards, because shit will happen afterwards, right? All kinds of things. It's just, I'm talking from experience is all. You start treating a boiler, you start maintaining it, you're going to get more issues up front right away. So that's all I'm saying. Okay, so effects of temperature on hot water heating systems. They talk about oxidation. And oxidation in your water process. Well, look, oxides produce rust. And like all chemical reactions, heat, so hot water accelerates that process. So that causes issues as well. Hot water lines are usually more prone to oxidation. And then hot water heating systems containing steel or iron components are subject to corrosion. It just makes sense. He knows he shouldn't call me. It's a fellow instructor trying to call me. Okay, so most hot water systems do not present a problem once the air has all been removed and you start up. But if the system is continuing receiving fresh makeup water, then you have some issues. The next thing in here is solubility. Temperatures affect the solubility of dissolved chemicals. Temperatures above 60 can result in settling out of temporary hardness that coats pipe walls. Okay, we talked about that. Density and expansion. An increase in temperature produces a change in density of water. It becomes lighter, doesn't it? Water is most dense at 4 degrees C, but that 4 degrees C of a mass of 1,000 kilograms. So if I heat that water up to 100 degrees C, the mass is less. So as you can see, the water becomes lighter. So that's where densities come in. Now they talk about hot water heating systems must have allowances for constant expansion and contraction. We talked about that. I think Marty is going to talk more about that. And similarly, we must have a way for relieving any pressure that may build up. Right? We have to have a pressure relieving device, some kind of safety valve when we're dealing with hot or high temperatures. Any questions? Okay. That brings us to objective 2. And we want in objective 2 to state the 3 laws of buoyancy, describe the effects of buoyancy on regular shaped objects submersed in water. But first, I want to share a short video with you. Okay, let me get this here. Optimize, make this big. Yeah. Okay, here we go.
Some of the best opportunities to learn are the moments in which we are perplexed, those moments in which you begin to wonder and question. These moments have happened throughout history and have led to some truly amazing discoveries. Take this story, for example. There once was a fellow named Archimedes. He was born in 287 BC in the city of Syracuse in Sicily. He was a Greek mathematician, physicist, engineer, inventor, and astronomer. One day, Archimedes was summoned by the king of Sicily to investigate if he had been cheated by a goldsmith. The king said he had given a goldsmith the exact amount of gold needed to make a crown. However, when the crown was ready, the king suspected that the goldsmith cheated and slipped some silver into the crown, keeping some of the gold for himself. The king asked Archimedes to solve the problem, but there was a catch. He couldn't do any damage to the crown. One day, while taking his bath, Archimedes noticed that the water level in the bathtub rose and overflowed as he immersed himself into the tub. He suddenly realized that how much water was displaced depended on how much of his body was immersed. This discovery excited him so much that he jumped out of the tub and ran through the streets naked, shouting, "Eureka!" which comes from the ancient Greek meaning, "I found it!" What did he find? Well, he found a way to solve the king's problem. You see, Archimedes needed to check the crown's density to see if it was the same as the density of pure gold. Density is a measure of an object's mass divided by its volume. Pure gold is very dense, while silver is less dense. So if there was silver in the crown, it would be less dense than if it were made of pure gold. But no matter what it was made of, the crown would be the same shape, which means the same volume. So if Archimedes could measure the mass of the crown first and then measure its volume, he could find out how dense it was. But it is not easy to measure a crown's volume. It has an irregular shape that's different from a simple box or ball. You can't measure its sides and multiply like you might for other shapes. The solution, Archimedes realized, was to give the crown a bath. By placing it in water and seeing how much water was displaced, he could measure the volume. Then he'd calculate the density of the crown. If the crown was less dense than pure gold, then the goldsmith most definitely cheated the king. When Archimedes went back to the king and did his test, the story says, he found that the goldsmith had indeed cheated the king and slipped some silver in. These days, using the way an object displaces water to measure volume is called Archimedes' principle. The next time you take a bath, you can see Archimedes' principle in action. And maybe you'll have a genius idea of your own.
Cool, huh? So in here on our ILM, it says, state the 3 laws of buoyancy, describe the effects of buoyancy on regular shaped objects submersed in water. So buoyancy in the plumbing trade right here, we use buoyancy on all kinds of different things. The primary example is a float ball that operates a ball cock in a water closet, right? And it floats, it rises and drops, and it opens and closes a valve. That's all it does, right? If it drops, it opens a valve. If it rises to a point, it'll close a valve. And we use buoyancy for that. Now, Archimedes' principle is reason that the buoyant forces acting on the body reduce the weight of the body equal to the weight of the liquid the body displaced. So we'll try to break that down a little bit more for you. Okay, now the 3 laws of buoyancy are right here. A body sinks in a fluid if the mass of the fluid displaced is less than the mass of the body. Number 2, if a body displaces a mass of fluid greater than its own mass, it will float. And a body remains in equilibrium, neither rising nor sinking, if the mass of the fluid it displaces is equal to its own mass. Now, let me just explain this a little bit more. So if I had a big bucket and it was full of water, I want to tell you that there is something called buoyant force. And I spelt that wrong. Okay. I think, well, no, maybe not. So the buoyant force, so anytime you put an object in a fluid, and we're going to talk about fresh water as our fluid for the most part. If you put an object in a fluid, the amount of water it displaces, so if this is completely square and this was full of water, if I put something in there, the amount of water it displaces will be equal to its volume. Okay, so this is kind of Archimedes' principle. For example, if this object right here was 1 cubic foot, and I put that in here, the amount of water that it spilled out will be 62.4 pounds. So you can see now the volume is equal in here to the amount it displaces. Now, if this object right here was, let me just change this number. If this object was 2 cubic feet, this object was 2 cubic feet, and I completely submersed that object in water, how much mass of water will it displace? Anybody know?
156 pounds.
It's going to be 2 times 62.4. It's 2 cubic feet. We know that 1 cubic foot is 62.4 pounds. So it's actually going to be 120.
124.8.
8 pounds. Right. So now, if we know that the comparison of buoyant force is equal to its volume, we can then figure out if this object will float or sink or be in equilibrium, as they said. So let me just do a couple of more examples here. First off, if I had my bucket of water and it's full of water right to the top, right? There's water in there. Okay, well, excellent. There we go. Let me just draw my box again. There we go. And it's full of water. And I took an object, and I'm going to say that this object weighed 100 pounds. Okay. This object that right here weighs 100 pounds. And I'm going to put that object in the water. So, and then I'm going to say that the amount of water it displaced, so the mass of water it displaces is 62.4 pounds. So I can determine by this that this object is 62.4 pounds while it's submersed in water. I can actually divide it by 62.4 pounds per cubic foot. And this object would be 1 cubic foot. But what I want to know is, because its volume is 1 cubic foot, there is a certain amount of buoyant force lifting up on that object. It's like a beach ball. When you put it in water, it floats because of its volume compared to its mass. Now, this object, I determined that it's 1 cubic foot, so it will have a buoyant force of 62.4 pounds pushing up on it because of its volume. So while this object in water weighs how much? So it weighs 100 pounds in air. And if I take off its buoyant force, this object weighs 36 or 37.6 pounds when it's immersed in fresh water. This is the only way I could sweep my girlfriend off her feet is in the swimming pool. So here's the worksheet that we're going to work on. So for all of the following questions, the fluid that we're using is fresh water. Now, as you may or may not know, salt water, like ocean water, is way more dense than fresh water. So that's why you get better floatability, if you will, depending on the salt content in the water. Some areas in the world, like the Dead Sea, you can practically walk on that water. Oh, wait, somebody did that already. Who did? Anyways, regardless of that, you can float completely on top of the water because of its density. Okay, that's what happens. So let's have a look at number one here. It says a block of material weighs 900 pounds and has a volume of 5 cubic feet. We have a density triangle where mass divided by the volume is equal to its density. So we will determine the density of this object by simply taking the mass and dividing it by its volume. So if you take 900 and divide it by 5, it has a density of 180 pounds per cubic foot. That's pretty easy. Now to find the relative density,
Can you share your screen?
And I'm not sharing my screen. Jeez, thanks for that. There, I'm already starting to write on here, and I'm sorry about that. So there's the density right here. So this is what I did. There's the density triangle. So now it wants the relative density. So we take the density of the object and we divide it by the density of water or air, depending on what that object is. And that will give us our relative density or specific gravity. So that means I'll take 180 pounds per cubic foot, and I will divide that by 62.4 pounds per cubic foot, and I will get the relative density. As you can see, relative density has no increments of measure. They all cancel out. And that has a relative density of 2.88. Now, I want to make a note here. Any object that has a relative density of greater than 1 will sink in water. Any object that has a relative density of less than 1 will float in fresh water. Okay, so that's another little sidebar on there. Now, C here says, what is the total buoyant force produced by this object? Buoyant force is directly, let me write this, directly related to the volume. So how much buoyant force is pushing up on that object is directly related to the volume. Here we have a volume of 5 cubic feet. So I'll take my 5 cubic feet and I'll multiply that by 62.4 pounds per cubic foot. So the buoyant force of this is 312 pounds of buoyant force. Now I can ask you that block of material that weighed 900 pounds in air, how much does it weigh when it's submersed in water? I could tell you that 900 minus 312, that block of material when it's submersed in fresh water weighs 688 pounds. So it's lighter because of its volume. So let's go to number 2. And I've written all over the sheet here. Okay, let me just get some space. So number 2 says an object that weighs 300 kilograms has a volume of 0.7 cubic meters. So what is the density? Density is taking the mass and dividing it by the volume. So let's do that. 300 divided by 0.7. So that is 428.57 kilograms per cubic meter. So what is the relative density of that object? What we do is we take the density of the object and divide it by the density of water. The relative density of this object is 0.42857. Is this object going to sink or float? It's going to float. Has a relative density right here of less than 1. It will float. So now what is the total buoyant force produced by this object? The buoyant force is directly related to the volume. 0.7 cubic meters is the volume. We multiply this by 1,000 kilograms per cubic meter. This will have a buoyant force of 700 kilograms. So this object right here is 300 kilograms, but I have a buoyant force pushing up on it of 700 kilograms. So this thing is gonna float right on the top of the water, is it not? There we go. Okay, we left off right here for number 3. What? Now for number 3 here, let me just give a different pen. Number 3, an object has a volume 9 cubic feet and weighs 17, or 9 cubic meters, excuse me, and weighs 1,700 kilograms. What is the density? Well, again, we take our mass and we divide our mass by the volume to get our density. And the density for this object is 188.8 kilograms per cubic meter. Now, to get the relative density, it says take your density and divide it by the density of water or air. This happens to be 1,000 kilograms per cubic meter. Remember, you have to match both of these numbers with the density that's appropriate. So the object's relative density, well, it's basically that. So it's 0.18888 times heavier than. Is this object going to sink or float? It is clearly going to float. It has a relative density of less than 1. So now we know what is the total buoyant force produced by this object. The buoyant force is directly related to the volume. So that's going to be 9 cubic meters multiplied by 1,000 kilograms per cubic meter. The buoyant force, this object is 9,000 kilograms. So how much does it weigh when it's submerged in fresh water? Well, the object weighs 1,700 kilograms, and we minus off the 9,000 kilograms off it. Well, listen, the object is not minus 7,300 kilograms. It means it weighs nothing when it's submerged in fresh water. It weighs 0 because you come up with a negative number here. It weighs nothing. But if I wanted to submerge it underwater, I have to put a pressure on top of it or a mass on top of it of 7,300 kilograms to get that thing to go under the water.